Hello friends, I'm Janaki Ghosh and welcome to my video series on exploring mathematics using spreadsheets. In every session of this series, we'll be exploring an interesting problem or phenomenon which can be explained using mathematics. Today, we are going to look at the birthday paradox. I'm sure everyone loves to celebrate their birthdays. I'm sure you do too. But have you ever wondered if there are other people who share the same birthday as you? Or how common are birthdays really? Well, today we are going to explore this problem. Suppose you were to throw a party. How many people do you think you need to invite so as to be sure that there are at least two people in the party who have the same birthday? The birthday paradox actually asks this question. So, how many people do you need in a group to ensure that there are at least two people having the same birthday? And asking the same question in a slightly different manner, how many people do you need in a group so that the probability of at least two people having the same birthday is about half? So I would request you to pause the video and think about this a little. So how many people do you think there should be, let's say in a room, so that you are sure that there are at least two people in that group who have the same birthday? When you ask this question to people, the initial reaction is 367. Well, the logic is that there are 366 possible distinct birthdays if you include 29th of February. And therefore, if there is a 367th person, then obviously that person will have a birthday different from the others. This is correct, and the probability of a match reaches 100% in about 367 people. However, in about 70 people, we find that the probability of a match is 99.9%, and hence the paradox. So, in around 70 people, you will always be sure to find at least two people who have the same birthday. Isn't that wonderful? Let us explain this using the concept of probability. Let us take the case of just two people. The probability of two people having different birthdays is, as given on the screen, 365 upon 365 into 364 upon 365. Well, this is because if there are two people, the first person obviously has a birthday on one of the 365 days of the year, and that is a certain event. So we can represent it as 1 or 365 upon 365. The second person must have a birthday different from the first one, and therefore there are only 364 possibilities for the second person. This product leads to 0.9973, pretty close to 1. So the probability of two people, randomly selected two people having different birthdays, is 0.9973. So if you want to find the probability that two people have the same birthday, it would be 1 minus this value, which leads to 0.0027, which is a very small probability. Now, let P of n denote the probability of a birthday match among n people. And we know that by our calculation that P of 2 is 0.0027. Let us see what happens when there are three people. In the case of three people, the probability that three people have distinct birthdays is going to be given by this product, which is 365 into 364 into 363 upon 365 cube. But if you subtract this from 1, you would get the probability of finding a match among three people, which is 0.0082, also a very small probability. Now, what do we mean when we say a birthday match among three people? When there are three people, it could be that two out of those three people have the same birthday and the third person has a different birthday. Or it could also be that all three have the same birthday. So 1 minus this probability gives the probability that there is a match among three people. So let us look at a generalization of this problem. In a group size of 3, we just said that the probability of a match is 0.0082. When we come to 4 people, in this product, in the numerator, we will have one more value, which is 362, and the denominator will have an exponent of 4, and the probability is 0.0164. Again, for 5 people, we will have one more term in the numerator, which is 361, and the denominator will have an exponent of 5, and this value is 0.0271. So if we generalize this pattern for n people, for a group size of n, what expression will we have in the numerator? So the product will start from 365, 364, 360, and so on, and will end up, the last factor will be 365 minus of bracket n minus 1. Why is this so? Let us look at the case. So let us look at the case of 3 people. I have 363 as the last value here, and this is actually 365 minus 2. For the case of 4 people, we have 362, which is 365 minus 3. For 5 people, we have 361, so this is 365 minus 4. And the number here is always 1 less than the group size. So for n people, I should have 365 minus n minus 1. Now, if I have to simplify this expression, I could multiply the numerator further by 365 minus n till 1. So if I multiply with this and also multiply the same in the numerator becomes 365 factorial, whereas the denominator has 365 minus n factorial into 365 raised to the power n. So this is the generalized formula for the probability of a match among n people. Well, one could use a simple Mathematica code which can be implemented in Wolfram Cloud for generating the probabilities of a repeated birthday for group size varying from 10 to 70. So in this code, as you can see, the formula that we've just derived in the previous slide has been inserted, and a table of values can be generated to see the actual probabilities from group sizes of 10 to 70. Now when we plot this is interesting, isn't it? So we see that as the group sizes increase from 10 to 70, by the time it reaches 70, the probability of a match is very close to 1. Here on the x-axis, we are denoting the group sizes, that is the number of people in a group, and on the y-axis, we are denoting the probability. So by the time we reach a group size of 70, the probability of a match is very close to 1. Now let us see what happens. For what group size will the probability be close to half? So let's say we have 0.5 here, and if I draw a line here and bring this down, so approximately in a group size of 23 people, the probability of a birthday match is around half. Now in this next slide, there are instructions for doing a spreadsheet simulation of this problem. You can follow the steps later, but first let me demonstrate to you how to get a spreadsheet to simulate the birthday paradox. So in this sheet, if you can see, there are 3 columns B, C and D, which are marked as month, day, and D will have the date or the birthday. I want to generate 70 birthdays because I want to check whether there is a match in those 70 birthdays. So I'm going to simulate the birthdays. One possibility is, of course, to accumulate 70 people from different places or to generate 70 birthdays by asking people for their birthdays. But here we are going to simulate it using random numbers. So first I'm going to create just a column of numbers. So I drag this up to 71. So I get the numbers from 1 to 70. Okay. Now in column B, I want to simulate the months, and the months must be integers ranging from 1 to 12. So I use the rand between command in Excel, and I say rand between 1, 12. And for the date or the day of the month, I will use the same command rand between but I will have numbers from 1 to 31 because there are some months which have 31 days. So if I select both and double click, I will get two columns. Column B represents the months and column C represents the days. So let us look at the first birthday. The first birthday generated is 28th of October because the month is 10 and the day is 28. The second is 27th of, well, this is August, and so on. But how do I check if in this list of birthdays, of 70 birthdays, if there is a match or not? So for this, it would be convenient if I could somehow convert the month and the day to a single number. And then if we have a single number, it will be easy to sort. So in column D, we will have a sequence of 3-digit or 4-digit numbers. And this can be done by inserting equal to 100, a formula which is 100 times the month plus the day. So when I do this, every sequence of month and day gets converted to either a 3-digit or a 4-digit number. Now notice that every time you tap on the Excel sheet, a new set of birthdays get generated. Now the first birthday is 17th of March. So this gets converted to a number 317. And if I double click on this, I get all the birthdays. Well, now what I can do is I need to sort this column to see if there is a match. So now if I right click on this, I copy this, take it to a new column, and I do paste special and only paste the values. So the previous simulation will get copied here, and if I press this twice, I will actually get a simulation where the birthdays represented by these numbers are actually arranged in ascending order. As you can see, the very first one is a match. There are two, saying 102 represents 2nd of January, and then there is 112 which is 12th of January, and so on, and there may be many more. If you want to try it again, you click on this column, right click, copy, go to another column, right click, paste, special, and insert the values. And once the values are in, you arrange this in ascending or descending order, and again you will find that there would be a match. Here I can see 227, which is 27th of February, and so on. There may be some sets which have impossible birthdays, but that can be ignored. So every time you simulate a set of 70 birthdays, you would surely find a match. So the spreadsheet just verifies that for us. However, the explanation is already rooted in probability, which you have seen in the previous slides. Well, with this, I would like to conclude this video session. In case you wish to expand your understanding about this problem, here are some resources. Thank you very much for a patient listening, and I look forward to having you on my next video session. Thank you, and bye-bye.